when you double the atomic mass of something, you reduce its thermodynamics. So it turns out that deuterium,
it's literally just heavier.
right? Well, it's heavier, but it has thermodynamic considerations. So what's the thermodynamic considerations? Well, on the hydrology cycle on Earth, that means that equatorial water has 150 parts per million when the rain falls. When you go to the poles, that's the most deuterium depleted water. It's right around between 130 and 140. Why does that make sense from the chlorophyll side of the story? Well, you want to have less deuterium in the water when you're chlorophyll so that you can make food. Why? Because the sunlight at the poles sucks compared to the sunlight at the equator. See, it's quantized. And when you understand that basic thing from the first semiconductor, which is chlorophyll, then you begin to understand why nature is making deuterium depleted water around this huge 30 million volt current. Why? Because she doesn't want that electric current to get out and electrocute things in your cell or go down through, say, nerve pathways or the neural crest cells and electrocute those things, just like I told you that a bolt of lightning does when it hits somebody in the back. It creates an electrical resistance.
So you've got this huge reservoir power, this electrical potential around the mitochondria, and basically the isotope that is present in a water molecule will dictate how much of that you can insulate against.
Correct. And then here's the beautiful part of the story. The other part of the heme protein that I know you learned but don't understand how it's the feedback loop for the GOE is CCO also controls apoptosis. So what does that mean? It means that when bad things happen inside the mitochondria, meaning that it can't handle the TCA cycle or it's Warburg shifted and things are not going well, the planned demolition of apoptosis gets rid of that bad engine. So that was the feedback loop from the great oxygenation event that happens over probably 1.2 billion years, if my math is correct, where we innovate this heme protein. And it turns out that's the thing that saves your life if you get oxygen toxic for some reason. So then you should do a hard stop and say, okay, Jack, what would make a TCA living mammal get oxygen toxic? Well, I'll give you the first one that everybody knows about. 1971, we sent, astronauts up to the moon. They got in the space capsule. We used 100% oxygen in their capsule, and they all died when they got a spark. Turns out that oxygen at really, really high concentrations is really bad. Now I'll give you number two that you may not know because you're not a doctor. Any doctor knows about this disease called ARDS. ARDS it's called acute respiratory distress syndrome. That's what most people died from in COVID. So when we give people with ARDS endotracheal tube and we deliver an FiO2, which is oxygen at a higher level, why do doctors do that? Because they use a pulse ox to see what your oxygen level is. They're taught what the biochemist tells them, that if your sat rate goes down, you need to give people more oxygen because we are TCA mammals. What the doctors don't know is that you have this little switch in you that Nick and I were talking about, that nitric oxide story. And it turns out that the pulse ox, okay, everybody who's a doctor now, and this is for you too, Nick, you think that the pulse ox is accurate to what's going on at the mitochondrial level. I'm here to tell you that the story that I've already laid out for you, that's not true. You know why? Methemoglobinemia is not picked up by the pulse ox. In fact, in critical care medicine, you have to have a special pulse ox to pick up this. Why? Because you can be fooled. And it turns out that ARDS, when you don't know this and you give somebody high oxygen level, you actually destroy every organ in their body. Why? Because of the mechanism I just told Nick. The electric current gets out, the bolt of electricity follows the path of least resistance in the body, and it goes and destroys other organs. Why? All because the doctors are not taught, because the biochemists don't know the story about nitric oxide and oxygen being quantized and being paramagnetic. And it turns out when you know this story and you're a neurosurgeon who decides to go back in 4 years ago to start taking care of all these people that are getting told they're going to die, and magically, I know how to fix this problem because I know about the paramagnetism of methemoglobinemia, and I know how to flip the switch using a paramagnetic drug. Guess what magically happens? FiO2s come down. We can get people off their dopamine drips. We can get them back. The family gets told that they're going to die, and next thing you know, they're walking out of the ICU in 24 to 48 hours.
What is the paramagnetic drug?
Methylene blue, my friend. I already told you that. And the reason why is because it changes the oxidation state from +3 to +2. What does that do?
Now you can use that oxygen.
Knocks off nitric oxide and allows oxygen to bind. Then the pulse ox is accurate.
Mm-hmm.
What did I have to do? I had to go back and teach every nurse and every critical care doctor that I worked with for 4 years that they really didn't learn the things that were really important, taking care of sick mammals who they all thought were TCA dominant people. I said, no, in fact, that lady right there, she's more like a salamander. Okay. If we had an electron microscope and we pulled her blood out, we would find out that most of her hemoglobin was methemoglobin. And I bet you we would even find in some of those people that they also have nucleated red blood cells. And I tried to get some of the ICU doctors to do peripheral blood smears on these people, and they wouldn't do it. And why did I do that, Nick? Well, this is something else you learned about in evolutionary biology that you haven't put together with this story. You know that the only cell in mammals, specifically humans, that doesn't have a nucleus is a red blood cell, correct?
Mm-hmm. Yes.
Also doesn't have any mitochondria, right?
Yes, that's my understanding.
Okay, so let me ask you a question. What do red blood cells in children look like that are inside their mothers? Do they look the same as yours and mine?
No, doesn't there have to be a difference because they have to be able to pull the oxygen from the mother's blood into the...
No,